Okay, thank you very much. Thanks for inviting me. And thank you for being here bright and early. So we heard a lot over the last 1+ days about symbolic AI, neural networks, and I think a lot of the ideas resonate very well with what we're doing at Elemental Cognition. This talk is different than many of the others in that we're talking about our startup and how we actually put these ideas together and have deployed systems in the world. So it's going to be more, I guess, maybe more engineering oriented than previous talks. So it's going to be about our LLM sandwich, which is how we at Elemental Cognition take neuro-symbolic approaches to solving complex reasoning problems. Am I hitting the wrong button? It's this arrow, right?
Yes.
Right.
Can you do it?
Yeah. Thank you. Yeah. So my first slide just kind of violated Michael's decree yesterday about not saying LLMs can't do something, but I made the slides before he said it. So we know that LLMs can't reason, but if you look at some of the recent titles of papers that have been published, they'll lead you to think that LLMs either can reason, or they think that if we spent enough effort, prompt engineering, it will eventually be able to reason. We don't take that view, and in fact, as Gary said, a lot of deep learning people are starting to come around and say, hey, maybe we can't do everything. And Sam Altman said recently that the main thing that LLMs are bad at is reasoning, and many of the valuable human things require some degree of complex reasoning. Okay, and this is something that very much we very much agree with at Elemental Cognition. And in fact, when we when Dave Ferrucci founded the company in 2015, the idea is to bring together fluent language processing and complex reasoning and have it do something that haven't been done before. So what happens when we put together reasoning and LLMs? So on the one hand, we have, let's say, reasoning engine, where reliable, complex reasoning based on formal and efficient mathematical algorithms, these have been developed over many decades. They are mathematically sound, they are reliable, they make use of many different types of algorithms to accomplish what they're doing. Why hasn't this been very mainstream and adopted? Because traditionally it has a high learning curve. It's not terribly accessible. In order to do this, you require deep programming skills, and also it doesn't really have a good API for you to build things on top of. So like you need to really get into the nitty-gritty in order to use it. And on the other side, you have LLMs. Right, LLMs are super easy to use, APIs very clearly defined, or you can go to a web page and see what it does and try it out. These are great for low-stake use cases. So you can generate, transform, and summarize using statistical methods. And also, obviously, it has limitations, right? So we all know what these limitations are. So now, what happens if we take a reasoning engine, which is very powerful, and then we wrap it up in LLMs, which are very good at talking to the external world, and have it be the bridge between the outside world and the reasoning engine? And that's what we did. So that's our LLM sandwich, which is our symbolic approach to solving complex problems. So here we take the EC reasoning engine, which implements a number of the mathematical algorithms, and also wrap it in LLMs. And this gives us an interactive and natural language enabled complex reasoning capability. And what this combo can do is that it can interactively and reliably solve difficult reasoning problems. We can get provably correct answers across different domains. It gives you total decision transparencies because of the way the reasoning engine reasons. It generates a proof, and we can use that as explanation. And one of the very key points is it can eliminate the need for high skills developers. And I'll talk about, this a little bit more and talk about how it kind of levels the playing field and allow more people to use this platform. And because it allows more people to use the platform, it also accelerates time to market for AI applications. The implementation is efficient, it scales well, and it's also much lower computation costs than LLMs. Okay, so let's dig into the LLM sandwich a little more. So in the middle, we have EC's multi-strategy reasoning engine. It does causal reasoning, deductive reasoning, and also can do constraint solving and optimization. So in order to use a reasoning engine, you got to have knowledge, right? So let's say on the left, we have a knowledge acquisition process where we're trying to get knowledge about the application domain. And this knowledge is typically either in documents, in data, or it's in an expert human's brain where you need to talk to the human to get this knowledge, right? This knowledge needs to get into a formal representation in order for the reasoning engine to ingest and consume, right? So this is where the LLM comes into play, where we build something that is to leverage the LLMs to bridge the gap between the natural language documents or humans with the formal language models, okay? And I'll talk about this. I know this sounds like very wavy, but I'll talk a little bit more about that. So the formal language model then provides the LLM, provides the reasoning engine with the necessary knowledge it needs to operate. Now we can deploy this reasoning engine as a solver for some particular application. And on the other end, we have knowledge delivery, which is at runtime. The people are going to want to talk to the reasoning engine to provide it with more information, more data, or to ask for a solution or an optimization, right? So on this side, we have a text-based or multimodal application, intelligent application, which is all. Okay. Which also needs to communicate with the reasoning engine in the same formal language that the reasoning engine understands. And here again, we leverage LLMs to convert what the users are asking for into the same formal language representation. Okay, so this is basically what the LLM sandwich is the reasoning engine in the middle that can do the work that is required to be precise and reliable, and the LLMs bridging the gap. So this gives us a system that can interact with users fluently in natural language. The results, because the reasoning engine is doing all the hard work of doing the symbolic reasoning, the results that we get are reliable, they're transparent, and they're precise, and the implementation is efficient. Okay. So if we put the sandwich together, so one of the things that you'll say is, okay, well, if the formal language is really just what the reasoning engine knows, right? So you can think of many programming languages where the people directly program that, right? And then you can deploy the LLM to translate from natural language to the programming language, right? We actually took a slightly different approach where we came up with a declarative language called Cogent, which is what holds the sandwich together. This is what is bridging the LLM to the reasoning engine. And Cogent has a feature in that it reads like natural language. It is a subset of natural language, and it's constrained and it's unambiguous. Okay, so just some examples. If you look at the right, an architecture optimization, you can define types. So you can have work centers, and you have cooking center, which is type of work center, and then you can have different types of work centers. And then you can define rules about these things that you defined. So a cooking center in the second line here, a cooking center may combine a refrigerator with a cleanup prep center. So that's defining relationships between objects. And then you can also define like a combination, a relationship, you can call it when a cooking center combines a refrigerator center with a cleanup prep, this is called a work triangle. And then you can go on and talk about work triangles. This is actually in kitchen design. There are actually guidelines about the work triangle, the distances between them. So that's why we define these, and then we can add further constraints about it. And at the bottom, this is an example about a constraint. So every refrigerator center is required to be against the wall, whereas the other work centers can be in an island or something. Right. So it has the advantage of being readable by any English speaker. And it is unambiguous and can be compiled down into what the reasoning engine can reason with. Okay. And on the other side, that's another example of staff scheduling, where we can talk about nurses and shift being covered by nurses and nurses being booked on a day. And then you can have business rules that talk about shifts must be covered by exactly where nurse can't be working more than one shift, and so on. Okay. So the advantages here is you don't need to learn a new programming language. You can precisely capture the business logic in an ambiguous language. And the big advantage here is that you don't need to be a programmer to read this and understand what the logic of the program is doing. And this document is essentially an executable specification, because the Cogent compiler compiles this into the logical forms that the reasoning engine can reason with. And finally, in a deployment sense, this is great because this is a single source of truth. Everything about the system is derived from this document, right? The APIs are generated from this document. The rules that the reasoning engine uses is generated from this document. So you know exactly what your document is doing. And when you change this document and save it, everything recompiles, data gets reloaded into reasoning engine, APIs get regenerated, and it gets automatically deployed. Okay. Okay, so now you might say, well, okay, you say that you don't need to learn a new programming language, and now you have this subset of English. But how do I know what the subset is? Isn't that kind of like a new language, right? So, but yeah, we agree with that, and that's why we actually built some tooling to help you make that transition. The advantage of it is because it's in natural language, LLMs are very familiar with them, okay? So we have this model builder assistance, which we actually have two different versions of it. And this is the first one where the user is taking the lead. The developer is trying to build a document from scratch. So this model builder assistance has access to our whole Cogent documentation with the syntax rules and examples. Okay, that is in the prompt of the LLM, and the user can write the document, and then when it has a question, it can ask the assistant. So here up to this point, so above the gray background is what you already have. You know that day is a type, shift is a type, nurse is a type. Nurses can be working a shift, and then we're scheduling for 5 days out of the week. So now the user says, I want to associate a department with every nurse, and we want to schedule, take departments into account when we schedule. Okay, so it says, how can I create a business rule that there are different departments that the nurses might work in? So then the LLM provides you with the steps that you basically need to take in order to add this set of constraints to your document. So you first define department as a type, then associated department with shifts, and then let the model know which department is relevant for a given shift. And then it actually writes the code for you. So here, this part about defining a department, and a shift may be in a department, and a nurse may work in a department. Okay, and you can actually just copy, if you like this, what it's doing, you can just copy it into your model, and it's just added and extends the model. Of course, the LLM doesn't always do 100%, and that is where the power of this English-like intermediate formal language comes into play, is that if you translate directly into Prolog or ASP or whatever, a normal human is not going to understand what that actually means. Here, you're reading English, and if the logic isn't translated correctly, the developer should know. And that's why we think that this is going to lower the bar for entry and allow non-programmers to actually use this tool. And also another thing that the model builder might do is if it can give you the cogent, and it can also link you to relevant cogent documentation, and so that you can learn and read about it. So this allows the developer to interact with the system to capture application knowledge in a precise and a formal specification. And you can iteratively edit with the writing assistant until you get it right, until you get what you need. And I should say that this editor also directly links to the compiler. So if anything doesn't compile, it'll let you know. And we do have autocorrection, which I'm not showing here. And it also, based on the model that you declared and what you're trying to do, it can automatically generate test data for you. So it can generate a number of nurses, a number of shifts, and you already specified departments. So, and generate sufficient test data so you can see what the program execution results are to see if it's in line with what you're expecting. I don't know why. So it's okay. So I mentioned that there are two different ways of helping the user. So that was a developer driven. The developer is trying to do things, and it asks the assistant when it has problems. Here is a case where the assistant actually takes it is the driver, and this is appropriate when we identify several verticals where a lot of these applications are appropriate for, because this is complex reasoning. We can think of things like supply chain management, complex travel planning, workforce planning, and all of these classes of applications that many different customers are interested in. So we can produce a vertical specific abstract model as a background, and the customers can interact with the assistant to customize it. Okay, I don't know if this is gonna be big enough for you to see. Can you guys see this? I can't actually tell. Probably not. So I'll just walk over this. So on the right is the same cogent document up until this point where it says custom application. So this is the background model. And you can see that it mentions employees, it mentions different types of positions, it mentions shifts, but nothing is instantiated. We know that these concepts are very common in these types of applications, but we don't know what your particular application has. So what the customizer does is it prompts you for all the things that you need to add to the cogent document in order for it to be a fully instantiated specification that is executable. So it'll start by asking, okay, what are you trying to do? What kind of employees do you have? And then you can tell it, okay, well, I am scheduling for a trauma center, and we have emergency physicians, we have ER nurses and surgical nurses and so on, right? So then what the system does is that it takes these, and now it's that it adds emergency physician as a position, general surgeon as a position, it adds 4 positions. So this is like customized for your application. Then it moves on to the next thing and say, okay, now I added these positions. Now how many shifts do you have? And do you want to name them? Right. So then we ended up adding like 6 to noon as a shift, noon to 6 p.m. as a shift, and so on. Okay, so it'll keep going and prompting you for all the things that you need to provide in order to complete this as a full specification. So this, the advantage is you have a predefined template. You don't need to start from scratch, so it's much less burden on the developer's side. And it also captures the common rules and constraints. So it'll prompt you for things instead of you having to think of them and maybe forget some of your constraints.
Yeah, for 5 minutes.
Okay. You can have a guided dialogue to specialize your specification, and also similar to the other assistant, you can have a dialogue interaction. You can ask it to generate test data and see if the system is performing as you expect. Okay, so far what we talked about is on the knowledge acquisition side. So basically what you need to build a reasoning system, getting the knowledge piece. Once you did that, now is runtime where you are trying to use the system and interact with the user. So we have an interactive application generation where we have default dialogue support as well as some multimodal support for scheduling. So basically showing you the grids of the results. You can do that in a staff scheduling domain. You can do this in project planning. And you can do it, like for another example is in travel planning, okay? And what this gives you is, like I said, we automatically generate APIs from the cogent documentation that we have. And these APIs can interact with the reasoning engine. So you can add requests like, I need to be in London on June 15th, or you can query the reasoning engine for, okay, what's my best solution? What is my best itinerary right now? It also has auto-generated conversational apps. So this gives us the basic dialogue template as well as the multimodal display. And finally, because you might update your API and you can also build on top of the basic UI, and then you can automatically update your application in real time, as well as the business rules if you found that it's insufficient. Okay, so this is just showing you how you put the sandwich together. You have a model builder assistant, you talk to the system, you acquire the knowledge, and then that derives a formal language model, which can then be compiled down to something that the reasoning engine can understand. The reasoning engine tries to solve your problem, and it generates solutions for you to show to the user. Okay. So basically what we provide is an ECAI platform where it has knowledge acquisition APIs, reasoning APIs, and has problem solving and discovery APIs. There's a pluggable LLM layer, and you can deploy in private networks or on the cloud and so on. At the top, you can have a enterprise application layer where you can build applications in logistics, healthcare and life sciences, and these are the application areas that we have built applications for. So let me just show you a couple of screenshots of some of the applications we've done. So one of the applications is with One World, the airline consortium, where they have a program that is go around the world. You can go from anywhere from 3 to 16 cities. To qualify for this fair, the rules are very complicated. There are 16 pages of rules written in English. And here are some of the rules here. Yeah, you can stop in twice in North America. You can stop twice in Asia. And then there are a lot of these have exceptions. You can do this except when you go to South Africa, something like that. Okay. So we convert these all into Cogent. And we also need to take into account is the customer's preferences. Like I want to go to Istanbul between Athens and Rome, and I want to spend 2 weeks in Tokyo, and I need to be in Lima on this particular day. Okay, we have actual real users who ask for these things. And also any 2 cities, because it's a consortium, they only have to do 14 airlines. So any 2 cities, there may not be flights that's served by these 14 airlines, or flights might have been sold out on a particular given date, and this changes in real time. Okay. So I think I covered those, and this is just a screenshot of the actual deployed system, where you're on the right, you have a panel where you can have dialogue interaction with the user, shows you a map of what you have. You give the system the cities you want. It tries to optimize it if you don't have any, while satisfying your particular requests. It gives you dates based on what you asked for, and then tries to find you flights. And anytime it runs into any issues, it'll backtrack and try and make any changes that could automatically resolve the problem that you're running into. A second application is in degree planning. So this is an application that is deployed at a university, which I can't tell you which one because of contractual reasons. So basically, this is an application that is basically trying to play the role of a university academic advisor. So students can come in, so the grayed out part on the top are the classes that the student already took, and the student wants to plan out the rest of their semester. So you need to know what the degree requirements are, the required classes, and elective classes, what the prerequisite relationships are. And the system actually gives you ideas, like once you have these classes, it tells you like, okay, for this class, you can swap out that class and put in one of these 2 classes, and you'll still satisfy the requirements. Okay, and you can also ask it based on this plan that I already have. Is there another minor that I can get with minimal addition to the schedule? So things like that. I'm going to skip the next application. Okay, so to conclude, I hope I convinced you, and I don't think that there was ever any doubt that LLMs can't reason, but I hope I've convinced you that if we build an LLM sandwich by adding a reasoning engine between 2 LLMs, that it can combine the reliability of the reasoning engine and the flexibility of language processing of LLMs, and make it a powerful reasoning solution for humans. And I showed you some deployed systems that show the capabilities of the applications built on this platform. And we also did an evaluation of our system against GPT-4. The results are obviously not surprising to anybody here, and in 3 different domains. And we have a report on our website. Thank you.
So we can take one quick question.
First off, this looks like a really awesome tool, something I'd love to play with. But I just was curious if you could comment on the security of such a system. So the prevailing threat model in cybersecurity is that if a user has any indirect or direct access to an LLM, they effectively have full control over all outputs. So under that threat model, and of course, there's like lots of mitigation strategies in the literature even presented at this conference. But to a capable adversary, all it takes is one pinhole vulnerability and the whole system's toast. Right? So with that in mind, like, do you think this kind of system can be secured to be appropriate for high stakes applications, or would you pause before doing that?
That's a good question. So one of the things that I think that makes this application work well is that the LLM outcome is not open-ended, right? So when we do that knowledge acquisition piece, the target needs to look like Cogent, right? So we accept results. We actually take the system generated statements and run it through the Cogent compiler. And if it doesn't compile, we try and fix it. Like, we don't just dump everything out in the output and show it to the user. And also on the knowledge delivery, so the application side, the LLMs are translating user requests into something that can be mapped to the generated APIs. So they are additions to the reasoning engine, queries to the reasoning engine. There's a very specific set of APIs that are generated based on the Cogent document that you have, right? So that, I think, constrains some of the output and hopefully can mitigate some of it. But like, we currently have a few applications out there. I think we need to keep an eye on it and see how well these boundaries work.